of the details that I put in. So yes, I'm going to be talking a lot about systems engineering, development, commissioning, operations. I joined the team literally 3 months before we launched the telescope, but a lot of the operations and systems design, is what makes everything work. So it's stuff I still know in the background, even if I didn't do all the ground testing myself. And the commissioning and operations, that's like making sure everything works, making the thing run. What do you do when things break? So that's what I do now. So your things in space, what do you do when things go wrong? So I'm going to talk a bit about that, and then I'll show some shiny science pictures at the end just to wrap it up. Yeah, so just a little bit about me. So I got my master's and PhD in astronomy at the University of Hawaii, which is a lovely place. I spent a lot of time up on a mountain in the middle of the ocean. That's Mauna Kea. So the reason you go to Hawaii to study astronomy is we have a lot of great telescopes there. So that's how I got my start, learning how to run telescopes. There's the Keck telescopes, the Subaru telescope, and the Gemini telescope in the background there on the mountain. This is me in one of the control room, one of the instrument rooms. The instrument's over here. This is a liquid helium and liquid hydrogen in order to keep things cold. We still use liquid helium in space to also keep things cold. So, same physics works. After I got my PhD at the University of Hawaii, I went and did what's called a postdoc research. So you get your doctorate, but you're still not considered smart enough to run things yourself. So people hire you on to work on their projects for a few years at a time to get more experience. So I did a lot of work on Palomar Mountain in California at the Hale telescope there. Again, learning more about how telescopes work and all that kind of stuff. Ground telescopes are great because that's where you get to do all your testing, because you can actually take things apart, put some duct tape, tighten a screw, which literally we've had to do to keep things running throughout the night. The trick with ground telescopes, though, you've got to worry about weather. So put things out in a dome, got to work about daylight. You can only run it not even half the time because you got to wait till it gets dark. That's a pain. Even when it is dark and clear and wonderful, you're still looking through the whole atmosphere. That's a pain. The atmosphere is what makes all the stars twinkle. So you're like, oh, the pretty stars are twinkling. That means you've got high velocity, winds that are making your stars twinkle. So beautiful twinkling stars means our images aren't stable. So the way to get around all that is you put telescopes in space. So after I did my extra training as a postdoc research in California, I got hired on at the Space Telescope Science Institute. So that's where I work now in Baltimore, Maryland. And that's where we run and operate both the Hubble Space Telescope and the James Webb Space Telescope. Like I said, you got to get above the atmosphere to get rid of all that pesky atmosphere and all that pesky weather that keeps getting in our way. It's great to breathe, bad for optics. So Hubble Space Telescope's been up there for 35 years already, still going strong. I use both of these telescopes for my science, and they operate well together, getting us different types of light. And then about 3.5 years ago, that's when the Webb Space Telescope started in operations. And like I said, I joined about 3 months before we launched. So just a very brief introduction to make sure y'all know what I'm talking about. In case you've forgotten, light is a very broad term. Electromagnetic spectrum is basically everything from gamma rays and x-rays, like you're getting an x-ray at the doctor, all the way to radio waves that you're using to do your communications. That's all considered light to an astronomer. They're just different wavelengths. So things like x-rays that go and image your bones, those have very short wavelengths. And then the radio waves that you need a large radio dish, those are very large wavelengths. And our eyes see this very little sliver of visible light. So I'm going to zoom in there. You can see visible light that our eyes can see, ultraviolet light, too blue for our eyes to see, and then infrared light, too red for our eyes to see. We're just looking at the stuff in the middle. But the Hubble Space Telescope that's already up there, let's do that, is optimized for visual light. So Hubble telescope sees what our eyes can see, but much better because it's in space and it's got a large mirror. And just for funsies, beautiful meerkats in optical light, nice fuzzy creatures. Webb telescope, optimized for infrared light. If you can tell, this is a slide I also used for first graders. Figured you wouldn't mind. This is what meerkats look like in infrared light. So, our eyes can't see the infrared, but we can build detectors in a telescope that can see in the infrared. If any of you have used infrared cameras, police use infrared cameras, great for tracking the heat. The other great thing about infrared cameras that I care about in space is that dust blocks the visual light, but the infrared light, like I said, it's a longer wavelength. It actually goes through the dust so we can see what's behind it. And we can see the heat glowing and where new stars and things like that are forming. So the combination of visible light from the Hubble telescope and infrared light from the James Webb Space Telescope can let us see kind of the whole picture of what's going on. So we really like the fact that they're both flying up there at the same time. We can learn a lot more science. So now I'm going to get a little more detailed because Stephen told me you want details. So why does the James Webb Space Telescope look funny? Why does it look the way it does? What are technologies that had to be developed to make it run? And then how does something like this get built, tested, launched, operated? That's what I do day to day. And how does this all work? And just as a just as a starter, this whole thing takes, from design to operations, takes 20 years. So that's why I said, I'm not old enough to have been doing this for 20 years. That's why I just get started. So yeah, why does James Webb look the way it does? Well, first, when you're designing any telescope, you always have to have, what do you care about in mind? Any systems designs, you want to know what your end goal is. So the systems designs for Space Telescope, for the James Webb Space Telescope, is we wanted to see really far away. And the reason we wanted to see really far away is because light takes time to get to us. So the farther away we see, the further back in time we're actually looking in the universe. Because farther away takes time to get to us, we're looking back in time. So it's basically like we have a time machine when we're using telescopes, which is pretty cool. So if we want to understand how galaxies and matter assembled throughout the entire lifetime of the universe, we want to look really far back to what we would consider first light, the very first stars and galaxies. And then anything between then and now is we can see kind of how galaxies assembled over time. Really far away means it's really faint. We need a big telescope. Also, like I said, we wanted to see through things like gas and dust. And that's important because we want to see how stars are forming in all of that dust. And we also want to see how planets are forming in all that dust. So we want to look at that. And then the other cool thing that we wanted to do with the new shiny telescope is we wanted to start understanding exoplanets. So those are planets around other stars, not our star, completely other stars. And, what we always want to know is, are any of these planets kind of like our planets? Are they very different? There's millions, billions of stars in our galaxy. They could all be very different. So the way to start learning about them and why we needed a new telescope is we want to know what their atmospheres are. Because if we know the elements in their atmospheres, we can tell, is there oxygen? Is there nitrogen? Is there sulfur? Is there potentially something on that planet that's interacting with its atmosphere, something growing? And all of that you can start to tell when you can tell the elements in an atmosphere. So to do this, we needed a new telescope. So what does this mean? It needed to be large because we wanted to be sensitive. So we have to have a large telescope to get a lot of light. The large telescope's also important because I said infrared light has a large wavelength. So the larger the telescope is needed for a larger wavelength in order to have good angular resolution. Angular resolution is just how detailed your images are. You don't want blurry images, you want fine detail. So we need a large mirror. Next, we need it to be cold. So everything emits an infrared light. You and me, like your infrared cameras, are all glowing in infrared light. The sun's bright in infrared, Earth's bright in infrared. The telescope itself is glowing in infrared. So we need it to be as cold as possible. And in order to get as cold as possible, we need it to be far away from Earth and all of us that are emitting light. So we can't have it in low Earth orbit like the Hubble Space Telescope is. So that's why, which I'll talk about a little more later, we put it out at this point called L2. It's a Lagrange point. It's far away. It's like 1 million miles away from Earth, past where the moon is. So very far. And we also need it to be stable, so I'll talk a little bit more about this as well. It needs to be really stable for all of our optics and all of our image quality. You don't want your telescope shaking when you're trying to take an image. It'll be all blurry if it's shaking on you. So this is a really boring thing, but this is what engineers make all the time. All of their mission requirement documents. This one's back from 2007. So we didn't launch until 2021. So they've been doing this for a long time, doing all your details of all the different requirements you need to get down to, you start with the science requirements and then you break that down into all the different engineering requirements you need in order to get to where the science is. Basically at the end, the things that matter is an instrument requirement, your optics requirement, your spacecraft requirement, that's how it moves, how it talks to the ground station, and how you get your data from it. So what this looks like is sort of your SketchUp of your 2B space telescope. You've got your instrument module at the back, you've got your optical telescope element up here, and this down here is the spacecraft element. So this is, generally speaking, a funny looking telescope, but all of the requirements went into it is why it looks the way it does. Then you also have the launch element, so it had to be launched on a rocket. It was launched on the Ariane 5, which was operated by our collaborators, the European Space Agency, and then it has the ground elements, so Mission Operations Center, that's where I work now, so that's Space Telescope in Baltimore, and then we operate through the Deep Space Network, and that's a group of large radio dishes at 3 different sites around the planet, which I'll show later. And so the big part of the spacecraft, you have a sun shield, because I said you gotta block all the sun, you gotta block all the heat, that's what makes everything work. And then this is the spacecraft down here that does all the actual flying now. Yeah, so like I said, the reason it built the way it is, it has to be large. We've never built something this large in space, which means it needs to be deployable. That means you have to be able to fold it up to fit in the rocket and has to unfold once you're in space. They'd never done this before, and it was a bit frightening to watch. In order to do that, it also needs to be ultra light. It's lighter than the Hubble Space Telescope, even though it's bigger than the Hubble Space Telescope. Like I said, it needed to be cold, so we're far away from the sun, so we can have radiative cooling down to about 40, 50 Kelvin. And then the instrument that I work on, which is at the longest wavelengths, the mid-infrared, we have a cryocooler to get even colder, down to 6 Kelvin is our operating temperature. Like I said, it needed to be stable, so again, far from the sun. It's at a stable orbital point, and then we also have a deployable sun shield to block all of the light from all of our optical elements up here. So this is the sunny side, and this is the dark side. And on the dark side is where all of our instruments are, and all the mirror is. Yeah, so as I mentioned before, this is Hubble, cute little Hubble. It's got a mirror that's about 2.5 meters across. And then this is Webb. Its mirror is 6.5 meters across. Like I said, we need it to be big because we're looking at faint things and we're also looking at light that has larger wavelengths. The other interesting tidbit, like I said, since it needed to be deployable, it had to fit at the front of a rocket. So once it's all collapsed down, it's actually smaller than the Hubble because the Hubble can't collapse down. So the volume that it has when it's stowed is actually smaller than the Hubble Space Telescope. And it's half the weight. So this required a lot of engineering feats, and I'll show you some pictures later, in order to get it down to that, so this could even be operational. And then Hubble Space Telescope's at low Earth orbit, which is actually great for Hubble because it meant that we could send astronauts to it to fix it because it didn't work when we first launched it. It also meant we could update some of the cameras and everything on it throughout its 35 years of operation so that we've been able to keep it scientifically up to date. The Webb telescope is not designed to be serviceable. I said it's 1 million miles away. We knew we would never be able to service it with any of our current technology, and so we had to make things in a way where we could fix its focus from here. So I'll talk about how we focus it, and we also had to make it in a way that we could try to have redundancies where we can. Yeah.
On that slide, can you explain what the less than and greater than 5 micron?
Yes. So that has to do with so this is what we're looking at. So basically what temperature is it. So the Hubble telescope basically operates because it's near the Earth, even though it's in space. The mirrors and everything are actually around room temperature. The less than 5 microns, so the Hubble Space Telescope looks at light that's 1 to 30 microns. Is the wavelength. So the less than 5 and greater than 5, we're talking about the length of light.
Okay.
So the bluest end of the James Webb Space Telescope can use radiative cooling, so that gets temperatures down to 40 Kelvin. And then I work with the mid-infrared instrument, which is all longer than 5 microns of light, and we need a cryo cooler that gets us down to 6 Kelvin in order to operate. Yeah, so like I said, we needed to be super light. So this is the density of Hubble up here, and this is the density that was the design requirement for the JWST in order to, so this is just the density of the mirror segments in order to account for just the weight budget in the whole system. So this took design, they started trying to do these design testing back in 1999. So that's when they actually really started to do some of the design testing for the cutting edge technology that would then be launched literally 20 years later. So with the design testing they did literally at Ball Aerospace is they decided that beryllium mirrors would be better than glass mirrors like what was used in Hubble. That's because they have low thermal expansion, they have really uniform temperature gradients, and they're just much lighter than glass. So that helps us get the weight requirement down. And so these are kind of the mirror segments. So they were being built from 2003 up to 2011. It's one of the primary mirror segments, so there's 18 of them. The secondary mirrors out at front. A tertiary mirror is to pick off and kind of push the light to the different scientific instruments, and then we have a fine steering mirror. And, in case you care about flowcharts, this was sort of the operations developments that they had to figure out in order to get everything built on time. So a lot of planning went in with all of the different subsystems. And this is just for the mirrors. And that's like everything could get built by the end of 2011, the beginning of 2012. And so this is a completely new optical design than any other telescope we used. It has 18-second mirror segments, and they need to be focusable after it's in space. So you have to move all your mirror segments around. It took a lot of literally sensing and phase retrieval, and they wrote a lot of computer programs went into this to try to optimize how to get the focus down to the right point when you're dealing with 18 segments. And each one of these mirror segments actually has 7 degrees of freedom that it can move. So that's a large engineering feat. Basically, they can move up, down, left, right, forward, back, and then they can also adjust the curvature themselves. So this bearing on the back, sort of these struts here, can tighten and adjust the radius of curvature of each of the segments so we can fine tune the focus. Like I said, this is a lesson learned from the Hubble that after it launched, it was not focused, and we could not focus it, and it would not have been focused if they couldn't send an astronaut up to literally put an extra lens in to focus the telescope. And part of that was because it turns out if you do all your testing in gravity, and there's not gravity, once you launch your telescope, you're in trouble. And so all of this testing had to be done with the knowledge that you're testing in gravity, but you're modeling it for what it will look like when it's no longer in gravity. I can put it in a vacuum chamber, but I can't take gravity away. So all of this focusing is so we can perfectly focus the telescope, no matter which direction the mirrors end up aligned in when we deploy them, because it's all folded up and we have to unfold it. And so we can even literally change the curvature to make it perfect. And like I said, lots of testing. So we didn't just wait for it to go to space to test it. The people at Ball Aerospace built a small version, a 1:6 scale engineering model, and went through the complete design testing to make sure that they can independently move all of these mirrors with all of the 7 degrees of freedom to get it perfectly focused. So the next new technology that needed to be developed is that, again, this comes from it needing to be light and thermally stable. So custom carbon fiber joints. So this is a lot of development that was happening at Northrop Grumman. They literally had to design new manufacturing techniques. I can't tell you what those manufacturing techniques are because it's Northrop Grumman. But they have their own manufacturing techniques, and they had to have time to develop new ones. So this is, again, why building a telescope, a $10 billion telescope that's going to be the biggest cutting-edge telescope we'd ever had, takes a lot of time, because you have to let all these people literally develop the technology to make it work. So they had to literally develop new manufacturing techniques and develop new techniques to even measure the structure and make sure everything was precise enough to get the sort of thermal controls and the weight constraints that they needed. All right, so now I'm going to talk a little bit about the different scientific instruments. And like I said, you always start when you're building one of these telescopes with the science in mind, because having this huge engineering feat is great, but then if it's just flying and not doing anything, you've just spent $10 billion for, I don't know, it doesn't really do anything, right? The whole point is we wanted to give us something cool with science. So yeah, as we said before, it's about 1 to 28 microns is our actual operating wavelengths. So we have 4 main science instruments on Webb. So this is the near-infrared camera, so that's up to 5 microns. The near-infrared spectrograph. So a spectrograph is anytime you have a point of light, you basically have like a prism or a grating that spreads it out into a spectrum, like the rainbow. And then that's important because, as I mentioned, we want to actually measure like the molecules things are made out of. So you do that with the spectrum. So this is like an image here, and this is every point of light is divided into like a little rainbow, but the rainbow's in infrared. And that's because each element has its own like fingerprint in a spectrum. It has its own like oxygen, nitrogen, helium. They're bright at very specific wavelengths of light. And so when we spread it out into the spectrum, we can figure out what things are made out of. So we don't just want pretty images, we also want to know the chemistry of how it works. So that's where the spectrographs are involved. This one over here is the near-infrared imager and slitless spectrograph. So it does, again, both imaging and spectroscopy. And then the mid-infrared instrument, again, is what I work on. So that's 5 to 30 microns. We have an imager, we have a spectrograph, and then we have a coronagraph. So that's for looking at exoplanets. So basically it has a black dot that you put the bright star behind so you can see the faint planets that are near your bright star. And the bright star would be too bright if you didn't have this coronagraph. It would drown down any signal from the faint exoplanets. So you basically put this black dot over where your bright star is, and then you can see the exoplanets around, or even just the planetary disk. This is kind of what they look like when they're on their test beds and getting built. The James Webb Space Telescope in general is a multinational plus corporation conglomeration in order to make all of this work. So NASA built the near-infrared camera. The Canadians from the Canadian Space Agency built our fine guiding sensors and this near-infrared spectrograph. The European Space Agency built NIRSPEC, or this near-infrared spectrograph, and a collaboration between the Europeans and NASA built the mid-infrared instrument. So it's really a multinational group that allows all of these different instruments to be built. And just to keep in mind the timeline, this is now 2012 to 2013 is how long it's taken to get all of these built. And someone asked about how many people does it take. So again, this is just a example for the mid-infrared instrument, plus the cryo cooler, because we need to operate at 6 degrees Kelvin. It's a combination of Europeans and Americans. So there was 2 leads. The European lead was at the UK Astronomy Technology Center in Edinburgh, and the American lead was at the University of Arizona. And then on the American side, what people were doing in the US, so this was in collaboration with NASA, the Jet Propulsion Lab in California, and Northrop Grumman. They built the detectors, the data systems, the flight software, and then the cryo cooler was actually built at JPL. And then on the European side, it's not just the European Space Agency, it's actually a European consortium of 24 different universities and astronomical institutes across 10 different countries. So it's a big organizational feat. And they developed a whole optical system and path that makes everything work. So just for this one instrument, it was over 200 scientists and engineers to get it built. So a lot of people. All right, so spacecraft and sun shield. So again, this is what the telescope looks like when it's all unfolded in its operational glory. So this is your 18 primary mirrors. They bounce and light off of the secondary and then down to the center. And behind this is where all your scientific instruments are. And then you have this big sun shield in order to block the light from the sun that's coming from this direction. And then, so this is now we're looking at the bottom side. So this is what the sun is seeing. So there's a solar array. You've got your antenna to communicate back with Earth. You've got your steering controls and your star trackers all on the hot side, the sun side of the telescope. And as I mentioned, it's 1 million miles away. So where is it? So this is Earth in low Earth orbit that you can't even see is Hubble. There's the moon. And then we're out orbiting the point called L2. So L2 would be in the Earth's shadow. We don't want to be exactly in the Earth's shadow because we need to power our electronics with a solar array. But we want to be near this very stable point. So this is a very stable orbital point. So we orbit that point. And that's also good because that means that all the hot things are on one side. So we can block all the hot things like the sun, the Earth, the moon with our sun shield. And so we have a hot and bright side, and then all of our optics and our scientific instruments are on the dark side, blocked by the sun shield. So what this looks like is we're orbiting this point L2. That's a very large version of Earth. There's sun. The very, not to scale version of Earth. Yeah, so we're orbiting the Earth's shadow is basically what we're doing, and we're orbiting the sun with the Earth. So yeah, so if you're kind of to zoom out, what our orbital path looks like is actually wavy because we're orbiting the sun, but we're also making a smaller circle as we do it, so we're kind of going up and down as we orbit the sun and stay just around the shadow of Earth.
So is this on the plane of the ecliptic? I mean,
Yes,
obviously.
yeah, so that we can be kind of in the plane of the Earth and the sun. Yeah, so across the ecliptic.
Does that limit what of the universe you can see?
It limits what we can see at any given time, but over the course of an entire year, the entire sky is visible because we're orbiting the sun with the Earth. So we have a limited about what we can see at any given time, given month. But over a year, we can point away from the sun, basically, and up and down, and see all the points of sky. We can never look to the sun because the whole point is we want to keep everything cold, and that would completely ruin all of the thermal design. But as long as we're always pointing away from the sun, we can see everything over the course of 12 months.
And that's using the full 7-degree range of your...
Yeah.
So your pitch up down to 7 degrees?
Yeah.
Okay.
Yep, exactly. Yeah, so this is the spacecraft bus. So like I said, we have some star trackers to keep track. You wanna know where you're pointed. We've got the station keeping thrusters. There's the solar array. Like I said, we need power to power all of our electronics. And there's actually a separate spacecraft and instrument computers. They're completely separate, run independently, because that just helps with, you don't want your instrument computers confusing your spacecraft. They're two separate, independent modules. And we'll go on.
What is used to power the thrusters?
Yeah, so what's used to power the thrusters is on this page right here. So hydrazine and nitrogen tetroxide thrusters, I can say that word. So that is what's used, the hydrogen and nitrogen tetroxide is what's used to power the thrusters.
So there's a limited supply.
There is a limited supply. So that is the only thing that's a limited supply on the telescope. What would be considered, at least in design, because you always design for things to go wrong. So what was considered a good lifetime of the telescope is if it could operate for 10 years. So in that, you include extra fuel in case the launch doesn't go completely white. Correct. A little extra fuel in case you need a little extra to do an extra station keeping to get into the L2 orbit. Everything actually went perfectly at launch, to the point that we didn't have to use any of those extra margins. So we actually have over 25 years of fuel. So now the question becomes, can our instruments last that long? And then that's my job to make them last that long. But yeah, so our limiting factor is no longer fuel because we've got 25 years of operations, and that's more than we even thought. Yeah.
The cryo cooler that you have to use to get down to
Yes.
Kelvin.
Yes.
What technology is used to get down to that temperature?
Yeah, so that's a closed loop system. So in the past infrared telescopes, it was a consumable, and so it ran out. Now it's a closed loop system. So at sort of general operations, you can get down to 15 Kelvin. Then it basically uses pressure. It puts it through a pinch point, so you pressurize the gas, and then it expands and cools.
So it's just like air conditioning.
It's just like an air conditioner, just in space. Yeah, literally just like an air conditioner. You compress it, it's just, you're compressing helium and you're compressing a lot more, so you can get down to 6 degrees Kelvin. But yeah.
What's the ambient temperature of 6 degrees that you're going for?
So the ambient temperature for all of the other instruments that don't have a cryo cooler is about 40 to 50 degrees Kelvin.
And what about space itself?
So it depends on if you have the sun beating on you and heating. So I think I've got that. No, I have that next. I'll have the temperature gradients next. So I can answer that better later in a different picture. And then it'll be better because it'll be a picture. Yeah, so this is your fuel supply. The other thing is that there was enough accounting, so we could actually use thrust for orbital maintenance about every 3 weeks, but we only need to do it every 6 weeks. So that also counts to better fuel management. And so like this is the actual more complicated orbit that we're in. So we're about 1 million miles away, but sometimes we're a little closer, sometimes we're a little farther. It's not a perfect circle. And the reason why you have to, deaccumulate angular momentum is because the sun and the photons literally shining on the sun shield pushes the telescope. Just the heat energy of that. So even if we weren't moving, we'd have to do some station keeping. Yeah, and then in order to get the data down from the telescope to us on Earth, we use radio waves. Great. And then we talk to what's called the Deep Space Network. So there's 3 separate stations on the Earth so that at any given time, you can see one of them. And so our speed is a 24 megabytes per second downlink and an 8 kilobyte per second uplink. So that's what your entire space telescopes run on.
But that's handling multiple satellites.
Yes, so I'll show that in a second. So yeah, this is your telescope, takes a really cool infrared image. You have downlink. This is actually the Goldstone station in California. That's one of the 3 stations. It sends us information in Baltimore. We get it there. Currently, we have a couple windows a day where we talk to the telescope, but we have to share with every other satellite, every other deep space mission that wants to talk to Earth. So we only talk to them about a couple times a day. During commissioning for 6 months, we had 24-hour-a-day contact because we were doing things for the first time. You're deploying all of these different systems. You move one thing and you wait to get confirmation that it moved correctly before you go to the next step. So for 6 months, we had 24-hour-a-day, 7-day-a-week shift work in order to commission the whole thing. Now we're in normal operations. We're talking to the telescope a couple times a day. Yeah, and then we send our commands to the Deep Space Network, then shoots it back up to the telescope. So, like I said, there's 3 stations. So there's one in Canberra, one in Madrid, one in Goldstone, and so that way, at any point in time of day, you can have contact with one of these stations. And I took this picture at about noon today. So about noon today, the James Webb Space Telescope was actually talking to the Canberra station. And this is what it looks like. So that, like I said, there's multiple dishes at each site. So you can actually go to this webpage at any time and actually see which satellites at which station and what mission they're talking to. So I literally went to this website, again, around noon today. Canberra was with the antenna number 34, was talking to the James Webb Space Telescope, and it'll tell you the range, so like how far away that telescope is. So at this time it was 3.4 million kilometers away, and it tells you the round trip speed time. So in order to talk to the James Webb Space Telescope, it's 9.29 seconds round trip. So that's how much time it takes to both ping the telescope and get a response of like, yes, I'm here, is 9.2 seconds. So it's actually not, it's pretty fast. You know, it seems like it's far away, but in terms of, you know, light seconds and light speed, it's pretty fast. And then this is the information around, you know, antenna 34 that was talking to at the same time. So like, what's it doing? Spacecraft telemetry, tracking and command. You know, the antenna does have a wind speed because we do care about the weather at the antenna. You know, the telescope does not have a wind speed, it's in space. But the wind speed is for the weather at the antenna. So yeah, anyone wants to go to that webpage at any time, you can also just Google Deep Space Network now, and it will get you to that webpage, and you can have fun. It's always fun to see when it's talking to Voyager. I forget what the round trip flight time is for Voyager, but it's much longer. All right, so this is the thermal design I said I'd get to later. So this is literally the thermal design of the telescope in order to keep it cold. So this took, like I said, a lot of engineering design to get it this cold. Each one of these so there's 5 different layers to the sun shield. So on the hottest layer, so this is solar input measured in watts. So that's the amount of like heat energy being deposited on the telescope. So 218,000 watts on the hot side. And then each layer reflects off more and more, and dissipates more and more of that heat. So the first layer actually gets rid of 90,000. The next layer gets rid of another 2,000. The layer after that, you're getting rid of a bit over 100. Next layer, like 20. And the final layer, you're radiating off about 5 until you get to the cold layer of the cold side of the telescope. So that's kind of I don't have actually, you know, heat in Kelvin. I just know the operating temperature of the instruments because that's what I work with. So the ambient temperature that the instruments work at on the cold side is like 40 to 50 Kelvin. But yeah, so that's sort of the temperature gradient we're dealing with. That's why we have 5 layers. Also, this was an engineering feat because, and very careful risk management in sort of the engineering design because the total telescope had 344 single point failures in deployment. This is why it was the riskiest thing we've ever launched for a space telescope. That's because if you are deploying a sun shield and it rips, there's no replacement for that. So when you literally have to unfold your telescope, there are certain things that go wrong and you don't have a telescope. The sun shield deployment, which is literally 80% of these single point failures, is a big part of that risk, but it is necessary to do the science we wanted to do. So 80% of your potential single point failures is just deployment and tensioning and getting the solar shield working properly. The other things were things like, you know, the secondary mirror was folded up and it had to fold down. You don't have a telescope if you don't have a secondary mirror for the light to bounce off and get into your instruments. That is obviously a single point failure. There's nothing around that. You know, you build in redundancies where you can, but the literal unfolding and deployment of the telescope has to work. And thankfully it worked seamlessly. Otherwise I would not have a job. So yeah, this is what the sun shield looks like. This is just one sun shield back in testing in 2013. So this is the full size. It's about the size of a literal tennis court. So it's 21 meters across and I think about 14 and a half wide. So this is basically the size of a tennis court. There's a little person for scale.
What what's in between the layers? Is it some kind of insulation?
Nope, air. Yep, just air. You're in a vacuum.
What
Yep.
material is the telescope membrane?
Yeah, I don't have the exact material memorized, so I can't get that one to you. Yeah, the passive cooling is just the solar shield. Yep, it's just literally, and then having the multiple layers, like I said, every layer reflects more and more of the heat away. The first one shield does most of it, but because we need to get down to a passive operating temperature for the near infrared of around, yeah, like I said, around 40, 50 degrees Kelvin, you need 5 layers of sun shield in order to do that. And I guess a little bit of the redundancy, you're only getting rid of like 5 watts of energy with the last sun shield. So that's about as much redundancy as we have with the solar shield. Other than that, like you do need all 5 layers in order to really reflect all the heat away.
Is that degrading over time?
Potentially. So one of the things that I do not have a slide for that I measure with the mid-infrared instrument is we're worried about we are measuring basically the background radiation. So in mid-infrared, that's where you measure anything that's hot. So the universe is hot in the mid-infrared. And we were worried that the background level was going up. And the potential reason for the background level going up would be holes in your sun shield. We've determined that we don't actually think it's going up. It was just poor calibration, which is great because we don't want holes in our sun shield. The other thing that we realized was part of the variability is it was literally variability depending on where in the orbit we were. So there are slight changes in the background radiation depending on where in the orbit around the sun we were. And those weren't in the initial models. So once we modeled that in and actually also corrected for some sensitivity and calibration issues with our detectors, there doesn't seem to be any large increase in the background. But that's literally part of my job is monitoring the background levels to make sure things like the solar shield isn't getting holes in it. Yeah, because that's the best way we have of testing for something like that. Our instrument in the mid-infrared would notice that first. So we're kind of like the first, but there's nothing you can do to fix it. You would just have to, compensate, exactly. All right, so I'm not gonna read all this, but this is just to show you the initial contract and, TRW is who we initially contracted with, which later merged with Northrop Grumman to do a lot of our testing back in 2002, and we launched on Christmas Day 2021. So, initially they wanted to launch in 2014. Let's just say they didn't plan for all of the engineering that needed to be done in testing, so then they rescheduled to launch in 2018. They didn't make that either, so then we rescheduled to launch in 2020, and then this thing called COVID happened, and we couldn't launch until 2021. But yeah, this is also why it literally takes 20 years to design, build, and test a space telescope of this magnitude. So now we're up in terms of building the telescope, we're up to 2013. These are all your different scientific instruments in their flight instruments module, as it will go onto the back of the telescope. Mid-infrared instrument that I work on is literally perched on the back of all the other instruments, kind of like a spider. It's got these trusses that come off of it and literally perch it off the back because it needs to be thermally separated from everything else because we keep it cooler. And we don't want any heat leaking off of these affecting us. So we're as far back on the telescope as we can get.
So you're right next to the shield?
We are on the back of the telescope. I'll point it out when there's a different picture that I can show. Yeah, we're so all the instruments are on the back of the mirror, and then we are the furthest away from the mirror on the back.
So closest to the shield.
Yes, except we're we're all the same height above the shield.
Oh.
Yeah. How do you test all of these different instruments? Well, you need to go to places like the Goddard Space environment simulator that has a big enough vacuum to do some of these testing. So a lot of the vacuum testing was done in 2013, 14, and 15. This is the back of the primary mirror. So the primary mirrors are going to go here, facing the ground. This is the back hub, and so the instruments sit on back of this, on the back of the primary mirror, and then the mirror will be back here. And this is 2015, piecing that together. This is putting all of the mirror segments on. So they currently have covers on here. They're not actually black. That would be very bad. So this is putting all the 18 segments on. And again, this is building this all together, the telescope assembly at the Goddard Space Flight Center. And this is now all of the mirrors are up and assembled, and it's assembled onto the back frame. And so this is the shiny bit. It's actually plated in gold because gold reflects infrared light better. So that's why we plated in gold. It's very thin plating. And so, like I said, for when you have it folded up to stowed to go into the telescope, this is the secondary mirror folded up. And so this is one of the things that had to fold down and deploy. And like if that doesn't fold down, you can't get lights through this center here, and your instruments are back here.
So how many times when you tested that would you fold and unfold?
Yeah, so I don't know exactly how many times they folded and unfolded it. I will say often they built duplicates of things because you want to fold and unfold. You want to run things to failure because you want to know, say, how many times can I turn a wheel until it breaks? How many times? This, at least, you only need it to work once, but so you don't actually have to test that to failure. But a lot of the other things, you build duplicates of it, and you run sort of failure tests because you want to make sure that it'll last the lifetime of your telescope. So yeah, I don't know how many times they specifically tested that, but other things you run to failure to try to break, or at least run to twice the lifetime of the telescope to make sure it still lasts. This is so this is acoustic testing. So this thing basically, it literally, because launching a telescope is very loud and it will shake all of your instruments, and you need to make sure no bolts shake out of place. So you have to do acoustics testing. This is packaging it up to travel to the Johnson Space Flight Center because they had a larger vacuum that we could test it in. So this is the even larger cryo vacuum testing center where we could test. So this is it unfolded. So I said they had to fold it up every time they transport it, but they unfolded it here to test the whole optical element together in the Johnson Space Flight Center. Fun fact, while they were testing this, there was a hurricane that kept people from coming and going. So some people were stuck and just kept testing, and some people that were supposed to go there and take over shifts couldn't get there. So some people got out of work and some people got stuck with a lot more work than they were expecting. So yes, how do you test a $10 billion spacecraft? You test everything on its own. You also, which isn't marked here, you build duplicates of things and you test them to failure. You cross-check everything. You plan the hardware, and you want to test like you fly. Unfortunately, like I said, we can't go into zero G. We can't have the whole optical path tested like you will in space. So what you do is you make a model like you fly, and then you test like you model. And so this is so you can get around the fact of we can't go into zero G. So this whole integrated modeling testing allowed them to build something this complicated that just would not have been achievable before. There had been no way you could test all of these independent elements. So 2019, we finally have the optical telescope array on top of your sun shield. Yeah, so as I said, the instruments are on the back here. They're all the same height away from the sun shield that's on the bottom though. And this is at least the optical array is in its folded up form. So the side pieces are folded up, the secondary is folded up. You would not get any useful light into your detector in this setup, which is why it has to unfold. And then the solar shield is deployed because they're doing some testing. This is what it looks like when it's all folded up. So the solar shield gets retracted in and then folded up on either side. And so this is what needs to fit inside the front of your rocket. That's 2020. 2021, this is the flight operations in Baltimore. So this is where I work. Everyone getting ready to go. So there were over 36 rehearsals over 18 months prior to launch of everyone just running kind of test simulations of as if things are flying. And occasionally they'd make things break on you and you'd have to fix it or figure out how to work around it. So testing as if we're operating the telescope, but the telescope's still in the ground. Like I said, this started 18 months prior to launch. I joined 3 months before launch. So I only went to the very last rehearsal. That was my onboarding procedure to the new job, is you get one rehearsal and then you get to launch a telescope. So that was very busy. All right, so yeah, this leaves a lot of stuff out of a lot of software, a lot of verification. Like I said, there's thousands of people that made this work. So I was looking up a number, probably over 10,000 people to get us to this point. And this isn't even just normal operations. This is just building and testing and everything between all of the different countries and all of the different companies and everything that did all of it. So now we're to Launchmas Eve. So this telescope launched on Christmas Day 2021. So since I was new, I was not working exact launch day. I was working on Launchmas Eve. So I had the night shift before launch. So I got to watch as the rocket, the Ariane 5, just sat there on the launch pad. And every hour we would have a full systems check where they would go down the list and you would just say, we're green and go. Excellent. Next thing on the list. And that was my 10 hours pre-launch. Then I handed off, so me and David handed off to the other 2 people that had been on there. So this is our actual engineer for Mary. He had been on there for at least 10 years by that time. So handed off to the actual experts in case, for launch. However, when launch is happening, the last thing they actually care about is your individual scientific instruments. Nothing should be happening with the scientific instruments. You don't have a telescope yet. If something's to go wrong, it's gonna be far more explosive. But we're just there to just be all of the systems check. Everyone had to be on hand for launch just to make sure, nothing went out of parameters. So then launch happened. Obviously, even though I handed off to other people, I stuck around because why do you leave 2 hours before launch was when my shift change was. So you stick around and watch the fun. So it launched from Curacao. So I wasn't on the ground watching. We were in Baltimore at operations. So in Curacao was where they were all stressed out before launch. Launch went well. The minute launch happened, now we get to work in Baltimore. So this is the missions operations in Baltimore. So this is where, launch day was all the flight engineers, and we were off in a side room. After launch day and after everything's deployed, this is the room that I spent months in during commissioning. And then through that glass wall is flight operations control. So flight operations control is where you actually send it's the last point where you send the command to the telescope in space. This whole room is looking at the commands and looking at the data, but we don't actually get to send the commands. Only the person in the flight control room, which requires, an extra layer of clearance that I don't have, get to send the commands. We see the commands, approve the commands, and then they send the commands. So it's just, you don't want this many people with a keyboard to the telescope. There's one keyboard to the telescope, and you have to have extra clearance to get to it. So that's launched. We have liftoff. This is after it's been released. It's still all folded up, but released from the end of the rocket. There's Earth. This is one of our last actual images of Webb. So happy launch day. Like I said, I got to hand off to other people and then just watch the launch through the glass. So that was fun for me. And now we're controlling and commanding from Baltimore. This is what it looks like on our, basically on our control computers. There's Earth, there's Webb. This is December 25th, 2021. At least that's how it's tracked on our computers. That's how we knew it launched. But like I said, this is one of the last images. So about 30 minutes after launch, it deployed its solar array. And a few minutes after this is actually passed out of the view of our camera that was on the end of the rocket. So it was really great that we actually got to see the solar array. The computers told us the solar array had deployed. It's really nice to actually have visual confirmation the solar array deploys, because if that didn't deploy, you don't have any power, you can't run any of your instruments. So that was the first single point failure, basically, of the telescope, having your solar array deploy. So now we're commanding from Baltimore, and like I said, you have to do all of this unfolding as it's traveling out to the Lagrange point 2, it's unfolding. So like I said, it's all folded up to be at the front of to be at the top of the Ariane 5 rocket. So at about 3 days, it's already unfolded 2 of its arms for the sun shield. The initial sun shield deployment was after 6 days. After 8 days, you've started to separate out the different layers of the sun shield and tension them. And so, this whole month was very stressful. I was just sitting there every day because every day one of these is multiple single points of failure. So I'd wake up, see what the telescope's doing, see that nothing broke, know that I still have a job. It was a very great month. That's basically what happened. And I'm just, passively watching the mirroring instrument slowly get colder as it gets farther away. I can't do anything else but literally log a temperature every hour. That was my job. And then just hope that everything else works. So it's about 8 days, your central layer separates. 10 days, the secondary unfolded. This is the point where we have a telescope. Not everything, nothing's focused, but we have a secondary, which means even if everything else breaks, we can get light into the telescope, so we could do something. The primary mirrors deploy about 13 days. We have another mid-course correction at 29 days to get to our orbit toward our orbit around to L2, and then a secondary another correction to get actually into the orbit around L2. And so it takes 30 days to actually get to our orbital point. And then over this, initial 15, 20 days is all of the unfolding. So the commissioning lasted around 6 months, 200 days. Deployment took around 30 days. Literally focusing and all of those mirrors getting to work together took another 90 days. Then we have about 100 days to actually do all of the testing of our scientific instruments. We're scheduled down to the hour and down to the day. You don't actually need to look at that, but that's what our day-to-day schedule looked like. This is what took 90 days, which was focusing the telescope. So as it goes through this, what flashes gold here is which one of these mirrors is moving to make that image look different. So right now we're moving all of them together to try to get them all as focused as we can. So now each individual mirror is getting focused, and now we're running through each individual mirror and bringing all the points of light together so that we can focus all of the 18 mirrors down to one point. And that, like I said, took a long time. So like I said, you had to model it because we couldn't actually do this on the ground. So this was our best case scenario model, and this was when we focused it. So this is the error in our wavefront sensing over each of the 18 mirrors. So we modeled that we would get down to 23.3 nanometers RMS, and we got down to 43, and we got to 45. So I said we did pretty good in terms of getting our focus as good as possible. And so this was the very first perfectly focused image with the James Webb Space Telescope. So that was the point of light you saw moving, was to focus on this really bright star. This is actually the best focused image of the telescope we will ever have, because turns out the longer a telescope is in space, it will slowly degrade, and so it will never be this good again. So this is the best focused image we will ever have of the James Webb Space Telescope in March of 2022. So this is me at the ground, in Baltimore during commissioning at our, control center. So like I said, I'm monitoring the mid-infrared instrument over here. This is actually shows our cryo-cooler system. This shows the different temperatures of all the mirrors. Everything is shaded blue, which means that these are all the telemetry numbers. It's shaded blue because that means we're not actually in contact with the telescope at this time. When they're not shaded blue, that means they're new. Shaded blue means they're stale. So let me show you, I think I've got, so this is another image that I had one of my colleagues actually take last week for me of the full image. That one I could take because it was stale and they were still having restrictions about what we can take. Now there are less restrictions on the screens we can take, so I had him take a new one last week. So I said there's only a few stale numbers that are shaded blue. That's because depending on our data rate, it doesn't refresh all the telemetry numbers, just the ones we care about. So this is our cryo cooler, and the telemetry numbers we get are basically voltages and temperatures, and we have to infer everything from that. We don't have actual cameras on the telescope, it's just voltages and temperatures. This is a little model of what it looks like, of what the telescope currently looks like. So this is what was changing every day when it was deploying. And this is where the telescope is pointed on the sky. So there's a bunch of different instruments, and the actual light path to them is slightly different. So you point to an area of sky, but the light to the different instruments is actually slightly, it's pointed, each scientific instrument is pointed at a slightly different part of the sky at any given time. So that's where it is on the sky. And this is something I thought you all would particularly appreciate. So we have a voice loop we had to talk over during commissioning. This was our cheat sheet. You probably wouldn't need this cheat sheet, but for those of us that don't fly airplanes, needed a cheat sheet for like Alpha Bravo, Charlie Delta. You probably don't need that. We also had, 6 pages of different voice loops we could listen to at any given time. If you're generally listening to flight control, I was in the instrument room, so I was listening to the what's called the Sci Chord, so the science channel. We had a separate MIRI channel if we wanted to talk and not, log up the other voice loop channels. So, like a common thing that we would say is, I might say SI lead, so I want to talk to the science lead that's in charge of my room. SI lead, this is MIRI on SI Chord 2. Would be something that I would say like this. So SI lead, this is MIRI on SI Chord 2. Meet me on MIRI chord. So we could have a channel and not, or so we could have like a discussion on a different channel that not everyone's listening to and bog up the airspace. And then this is also what we do all of our systems checks on. So the science instruments room lead would go through each instrument, and we do hourly checks just to make sure there's no red things on our screen. So literally they'd call us all out like MIRI, near spec, ACS, and so they'd say MIRI, and I'd say MIRI's green and go. Near spec's green and go. And if something was wrong, you tell them something was wrong. Literally these lights would start flashing red if they were a number they shouldn't be. So it's very hard to miss when something's going wrong. Like I said, I literally mapped the temperature for 2 months of night shifts every hour. That was my very boring job as a PhD, logging the temperature of MIRI. We care a lot about the MIRI temperature, so all of these different lines is watching all of the different other instruments passively cool down to their operating temperature of 40 to 50 degree Kelvin. MIRI is specifically interested in not cooling as quickly as everyone else, which is, you would think why, and that's because we want to be sensitive to water. One of the scientific goals is to be able to see where water is. If water freezes on your detector when other instruments are outgassing, that would be a bad thing and you would no longer be sensitive to water. So we let all the other instruments cool down past what is called the water band. So that's where water would immediately crystallize if it existed near you. So we let everyone else cool down. We waited a bit, made sure everything was stable, and then we quickly cooled down, turned our heaters off, and then quickly cooled down and cooled down much colder than them. And that's just to make sure we can continue doing what it is we want to do.
When was that learned?
I learned it before this launched. Yeah.
Who?
I don't know who figured that out. Yeah. I will say if you don't do that, you can potentially, like I said, get water accumulate on your instrument that you want to be able to detect water with, and that's a bad thing.
Yeah, some genius thought that up, I guess.
Yes, and I'm very glad they did. Yeah, so as I said, the optical path to all of the different instruments is slightly different. So this is what all of the instruments pointed around the sky look like. So we've got the near-infrared camera, the fine guiding system, the near-infrared spectrograph. I said the spectrographs, makes all the little rainbows so we can find all the elements, and this near-infrared slit-list spectrograph and imager. And like I said, you have redundancy where you can. So there are two near infrared cameras. That's because we use the near infrared camera for focusing. If one breaks, we want to make sure we can still focus. So it's great for science. That just means I get two detectors to do my science with, but it's important to have redundancy there. The other redundancy is we have two fine guiding sensors because you need to be able to guide your telescope. So if one breaks, we still have a second. Other things, if my mid-infrared detector breaks, all the others still work, so we don't get two of them. We only get one. But the mid-infrared, as you can see, is where the dust starts to glow. So you see all this wispy stuff, and you just see stars over here. So yes, some challenges along the way. At one point in time, we lost contact with the telescope for a very frightening weekend, and that's because someone accidentally told the telescope to talk to us at a different wave band to the ground station than it was supposed to. They didn't know that's why, but we were pinging the telescope, and the telescope was pinging back, just not at the radio frequency we were looking. So that was a very long weekend. I didn't have to figure that some out. The grounds team figured that out, and thankfully they did. Another, unexpected things, there's weird scattered light you don't plan on, but when there's new weird artifacts in your detector, you get to name them. So this is called Dragon's Breath. There's a bright light, a bright star off the edge of the camera, but it scatters onto it. These fun little things are called wisps. That's because there's light coming off axis and bouncing off a secondary mirror strut onto your cameras. Basically, you can get around this by looking farther away from bright stars, or just knowing what it is and knowing it's not science is the important thing. I am in charge of the mid-infrared medium resolution spectrograph. We had to turn our instrument off for a month when the grading wheel randomly increased friction. And like I said, we don't actually have a friction measurement in our telemetry numbers, but we have voltages. So the voltage spiked when you tried to turn it. The voltage spikes when you're trying to turn it. That means it's harder to turn than it should, and it went into what's called safe mode. If anything goes out of sort of your green acceptable range, it just stops doing what you're doing until we on the ground figure it out and tell it to do something else. So we had it turned off for a month. We talked to all the ground engineers being like, why do we have high friction? They're like, this just happens sometimes. Like, well, that's not great when your thing's in space, it can't just happen. So the final decision after talking to ground engineers for a year was to try rotating it in the opposite direction. That was a very high-tech solution for a very high-tech space telescope. Thankfully it worked. So they think the root cause is from basically bearing cage precession. We can't know for sure because I can't go in and see what's actually going on. So now our solution is we just operate it in this nice little sweet spot with low friction. If we turn it 10 rotations in one direction and 10 rotations in the other direction, we've got this nice low friction zone that we're just living in now, and it's working really great. But that's the kind of thing you have to do when you can't actually open up and figure out what's wrong. NERIS had an issue where a cosmic ray hit their detector at an inopportune time and they couldn't talk to it anymore, so they turned it off and on again. So that's a very, very high-tech solution for that one. And then the current thing that I'm spending a lot of time on is the longest wavelength region of our near-infrared detector is losing some sensitivity. That's not something we can fix, but we want to know why. So we think it's from high-energy cosmic rays that just we don't have on the ground, and they didn't completely test all of the energies. It seems to be degrading basically our long wavelength grading, which is why it's affecting just the long wavelength end. And so this is something that's currently being tested on flight spares. So I'm not actively testing it, I'm keeping things running, but other people, other engineers are testing things on flight spares of the detectors and the gratings we have. So one fun thing that they're doing, for those people in the medical field, they're actually got some time on a hospital cyclotron facility in Manchester, England, to shoot some high energy protons at our detector. So this is the very highly scientific setup they have to shoot some high energy protons at the detector. So this is something that you would use to give yourself radiation treatment for cancer. So they're using nighttime hours when people aren't getting cancer treatment. They've actually got just 3 to 4 hours of beam time to shoot some high energy protons at the detector. Higher energy than what was initially in the testing design, because they're like, oh, we don't get that many high energy photons. We don't need to test that. Turns out you might not need that many high energy photons to do some degradations to your very careful coatings on your detector. So this was literally scheduled to be tested September. I don't know the results yet. I'll probably find out next month. So that's exciting. So like I said, you test what you can on spares you have because you can't actually poke the things in space. The other super surprising thing that happened in May, only 5 months after launch, while we're still in commissioning, we got hit by a largish micrometeorite. So this was larger than expected. They knew micrometeorites are out there and you're gonna get hit. We have a huge unprotected mirror, but this was larger than expected. And so you very quickly start to wonder, is this just unlucky or is this gonna happen every 5 months? If it's gonna happen every 5 months, we're gonna be in trouble. Thankfully, it's only happened not quite this large, but another large one has hit us since. So 2 every 3 years is basically what we're dealing with. It's something that this is where having your deformable focusing all your independent segments independently is very helpful. So this is now our best focus of our telescope. It was this at 45 nanometers RMS. We're now at 59 nanometers RMS. So like I said, that image I showed you before is the best image we will ever have because we will continue to get hit by micrometeorites. Right there where it's bright, yes, you can see that's where the mirror was dented. So before over here, the wavefront error only went up to 200. Now in that spot where it got dented, it's at 1,000. So we've now got another spot over here, not quite as bad, but visible. And so that's just gonna happen every few months. It's still very clean images. Like I said, your actual nanometers and change is not that bad, but this is why it's good to be able to refocus your telescope. So like I said, there's been pleasant surprises. All the deployments went literally perfectly. Our orbit's great. We now have fuel on board for over 25 years. We have great image quality. We now only need to do mirror corrections every 6 to 8 weeks. We had budgeted for every 2, so means we can be more efficient. Also, like our station keeping, we only have to do every 6 weeks instead of every 3 because our orbit's so stable, and our sensitivity is actually, except the long wavelength that I told you about, is actually better than expected. So everything, apart from the random things that just happen in space, is going very well. So yeah, that's the people at Space Telescope that keep it running. And then this is just to show you the image quality improvement we get. So these two are previous infrared instruments. So this is the point where I'm going to show some pretty pictures. This is the WISE telescope. It had a diameter of 40 centimeters. The Spitzer telescope, was twice as big, diameter of 85 centimeters. Your image starts to get sharper. But now we have the Webb telescope with a diameter of 6.5 meters, or if we're dealing in centimeters, 650 centimeters. So this is why the images are better than anything we've ever seen before. And we can literally see science that was just impossible before. This is the level of improvement we got with all of these engineering feats.
What time frames were the WISE and Spitzer operational?
So WISE was actually operational until recently. Spitzer, that stopped operation probably 10, 15 years ago.
Okay.
Yeah. And these were the first science images that were released after commissioning, just to show you some of the pretty pictures that got released with the Webb telescope. So this is a gas cloud in our galaxy. These are galaxies interacting. This is actually a star with a nebula around it, and just all of these fine structures, and everything would have been completely impossible to see with the telescopes we had before. And as I mentioned, we wanted to be able to detect signatures like water. So here's one of the first spectrums we took, and we are able, we actually got better calibration now, so the spectra look even better than that now. But we're already detecting signatures of water 6 months out. So that means we protected that. All of the careful cool down works. This is just an example. Like I said, we want to use both Hubble and the Webb telescope together because we look at different types of light. So this is what the planet Neptune, our 8th planet, looks like with Hubble. It's pretty, it's blue. That's what our eyes would see. this is what it looks like with the Webb telescope in infrared. So as I said, infrared is where dust glows, so we can see it actually has a dusty ring around the planet. This is a star-forming region in Orion. So stars are formed in very dusty regions. Where stars are forming in galaxies is actually where I study. So I want to see where the stars are forming, but there's a lot of dust there. That's why there's stars forming there. So you can't actually see until we go into the infrared. And this is the exact same region with Webb. And like I said, the resolution that we get in this image is because the telescope is so big. And so we see all of these stars that were just completely hidden in a screen of dust before. And then we even see this sort of shock wave in the edge of the cloud. And that's because there's actually a bright star over here that's pushing the gas and forming the shock wave. And so this dense gas is then where you have the new stars form again. So this is literally one of the galaxies I study. And so this is an image taken with the Hubble Space Telescope. And so I study stars forming in other galaxies. And so as you see in an optical image like this, there's all these dark dust lanes. And all of these dark kind of spidery patterns you see is because that's where the dust is really dense and it's blocking all the light from the starlight behind it. But where this dust is dense is where I'm interested in, because that's where all the new stars are forming. So this is again the Hubble image with all the dark regions from all the dust. And this is the same galaxy, but in infrared, and actually mid-infrared is where all the dust is now glowing. So we see all the dust glowing, and when it's glowing in different colors, that actually even tells us the different size grains of the dust. So I can tell you if there's large grains or small grains. Where it's glowing the brightest is where the new stars are forming. So we're seeing through the dust to where the new stars are forming. And so you get these big bubbles in the dust, and on the edge of the bubbles is where you have a lot of this new star formation. So I can use this to study how stars are forming in galaxies, both spiral galaxies like this, and I even study galaxies that are smashing into each other, and learning how the different stars are forming in these different galaxies. So this is kind of a wrap up. So obviously we learned a lot in building a state-of-the-art telescope. Literally we learned we can launch, unfold, and finish building a telescope in space, and it'll still work. We've never done that before, and it's amazing that it worked. Integrated modeling was needed in order to make sure we didn't have the same problems we had with Hubble of, model it like it's going to be in space, test, and make sure everything works together. Also, early investment in these new technologies is important. And then this is also a generational mission. So like I mentioned, it was 20 years for development, testing, and building, and now we have 25 years of operation that's just starting in 2021. So it really is one generation handing off to the next. And like I said, big telescopes like this don't get built without collaborations. So collaborations between countries, between different universities, between different companies. That's what you need to build a big telescope like this.
So how did that work?
Which part work?
Well, so you've got.
Because that's the last slide.
You got the European Space Agency,
Yep.
you got all these countries.
Yeah,
I mean, it was obviously successful at the end.
yeah.
How much pain was involved to get there?
I'm sure there was a lot of pain along the way.
Who freaked out?
Yes, I will say, thankfully that pain happened before I came, because I came 3 months before launch, so they knew it was going to happen, and they knew they needed another person to help with the operations. So yes, there was definitely, like I said, we had to reschedule the launch twice. Obviously, there was a lot of people mad about that, including our Congress, because they're also paying to have this telescope built, but so are the Europeans, and so are the Canadians. Every time you have to ask for more time, it means there's still more testing to do. It means it's going to cost more.
So everybody was on metrics, though,
Yeah.
as opposed to Mars.
Who was the ultimate customer who said 20 years from now, I want this to be able to do that?
Gotcha. So when we very first started, like I showed, you always start with what's the science you want to do. And in order to, because that decides how you build your telescope. And so those are the astronomers. So the astronomers, so I'm an astronomer, half my time I do science, the other half of my time I help with this telescope. So they ask astronomers of if you could build the biggest telescope, what's your dream? What do you want to do? So astronomers in the US, astronomers in Europe, astronomers in Canada were basically the three customers because those were the three countries buying into it.
Thank you.
Yeah.
I see the company name Ball up there.
Yep.
Were they in optics?
Yeah, so I think, Ball did a lot of the optics, so they built some of the optic tests, the initial, like I showed, the smaller scale version of the optics design. Yeah, so Ball and North, like I said, it's also a collaboration between some companies that we contract out to. Ball and Northrop Grumman as well. Yeah.
So are they in the process of designing what the next telescope will
Yes.
do and be and
Exactly.
what project?
Absolutely, because it takes 20 years. So there's already been sort of, like I said, the initial, science goal design. So actually, even a few years ago, they've already started okay, what do we want the next big telescope to be? Starting to talk to the astronomers, because then that'll drive the technology that needs to be developed. So the next big telescope that they want to build, they already have a name for it, at least a placeholder name, called Habitable Worlds Observatory, and that's going to look in the UV, the ultraviolet. So with Webb, we are focusing on looking at the infrared light, redder than our eyes can see. The next telescope, it wants to look at the ultraviolet, so bluer than our eyes can see, because we already have Hubble looking at the visible light. And so that'll give us a new part of the spectrum, and new insights into things that neither of these telescopes are currently giving us.
Are you able to make any comments, Kirsten, on the fact that they found a galaxy that shouldn't be there just after the Big Bang?
Yes, so one of the, like I said, scientific goals is to look for the first galaxies. I will say when you're trying to look at first galaxies and you're looking farther and deeper than you've ever looked before, you're gonna find things that are surprising. So they are finding, these galaxies, very distant, which means they're very young. They're not exactly what they expected them to look like. They seem to have more massive black holes than they expected, things like that, which is how do you grow a black hole that fast if you're not, if there hasn't been much time yet. And part of that, I'll just say, we have our models from what we knew, and so we need to redefine our models of the universe to fit what we now know. And every time you have a new telescope and you're looking in new places, it's not surprising you find things you don't expect. In fact, you expect to find the unexpected. If I only found what I expected, I wouldn't need to build a new telescope. So, yeah.
What's someone like you do for a hobby?
So Jason and I like to go hiking. We play board games. We also like shiny rocks. I do like shiny rocks. Yeah, if I wasn't an astronomer, I'd probably become a geologist. At one point in time, I wanted to be a paleontologist, so that was my other life goal as in first grade. So I like shiny rocks. Looking down instead of up is what I do for a hobby.
What's gonna happen once the propulsion runs out?
Yeah, so once the propulsion runs out, we can no longer keep a stable orbit in L2. Generally speaking, the last thing you do with a telescope, so this is the last thing they did with Spitzer, is you use the last bit of propulsion you have to make sure that it's in an orbit where it will never hit Earth. So, and then you also want to make sure it's in an orbit where it's not where you want to put other things. So I don't know exactly what the terminal orbit of Webb will be, but that's what you do with your last bit of propulsion. So the last bit of propulsion they had for Spitzer is they launched it toward the sun. Because it was in what's called an Earth trailing orbit, which means Earth would eventually catch up to it, and you don't want to hit what you launched. So the last bit of propulsion is to make sure it will never be in your way.
So how did you end up working at Webb?
Yeah.
What was that process like to get there?
Yeah, so the process was to get to Webb is, I first in undergrad was studying physics because I just like to know how things work, and astronomy was actually a hobby at the time. Then I did some astronomy research. I'm like, oh, I can actually like make a career out of this. It doesn't just have to be a hobby. That's great. Let's do that. And I get to go to Hawaii to do it. Even better. So then I did my my extra schooling, so master's and PhD out in Hawaii. And so part of that, Hawaii is known for all of its great telescopes. So starting in Hawaii meant I got a lot of experience working and running telescopes, understanding how detectors works, because that's where they actually built some of the first infrared detectors was out in Hawaii. So that got my base skills started of like being able to run telescopes, being able to know how detectors work, you know, and all that kind of stuff. Then I went and got a job, like I said, it's called postdoc researcher. So you have to do a couple of those of kind of like small research positions to learn, to get more experience. And I did that at Caltech and IPAC. And so, yeah, so there I also helped commission another instrument for Keck. I helped test an instrument at Palomar Mountain. And so again, that just got me more instrument experience. So when Webb was looking for a new astronomer to join their mid-infrared instrument, and I'd already helped commission a near-infrared instrument, which is the best you can do on Earth. That's how I got the job, basically.
Okay.
So, yeah, so the experience of all the ground-based telescopes I had through my schooling and then my extra research is what got me the experience I needed so that when they were looking for another person to join their team before launch, that's how I got the job.
Got it.
Yeah.
Wow.
That's right.
Yeah.
Wow.
Great job.
Thanks.
Very cool.
There you go.
Thank you, Kirsten.
Yeah,
Thank you.
very much. Wow.
Turn that puppy on for me.
Oh, shit. There you go.
Kirsten, thank you very much for coming and sharing your adventure with us. It was really terrific. I thought it was going to be good, and it was really good. And everyone else here, would you please help by putting the chairs away, putting the tables away, cleaning everything up, and try to get this whole thing wrapped up. Thank you very much for coming. It was very successful.
Like, all right, that works, still have a job. All right, next day, still have a job. We'll tell you. It's amazing. Oh, yeah. Better than it never happened. It never happened.
So none of those single point failures occurred?
None of them occurred.